All right. So yesterday we have discussed about the normal distribution properties, and today we are going to understand. So what are the practical applications of the normal distribution? Where do we apply practically? So let us discuss that aspect today. Right. So now let us apply this normal distribution concept on a topic called stock prices, and let us see how we can analyze and what kind of information we can extract, we can generate. So when you apply the normal distribution concept on this stock price, to understand the normal distribution and its applications, so uh, let us extract the data, the daily returns of stocks traded in Bombay Stock Exchange, BSE. So imagine that just you want to understand, so out of the two stocks like BML and Glaxo, you want to understand which stock is a more risky stock and which stock is going to give you more returns, so daily returns. So that is what you want to analyze, and based on that you would take a decision and you would invest the money into that stock price or into that stock. So for that purpose we have taken the data from 2010 to 2016 from BSE. So this is the publicly available data. You can also extract this data, and the data is like this. So this is for BML, date open, so at 9:15, right? So AM, how much is the price of this stock, and the day high, day low, the last trade price, and the closing price after adjusting few things, right? So then the total trade quantity and turnover of that company. So out of all these columns, so we are interested in the date column and then the close price. These are the two columns we are interested in, and based on this, so we are going to find out which stock is a riskier stock and which stock is going to give you more returns. So that is what we are trying to find out. And the same the data that we have collected from the Glaxo company also, Glaxo stock also. And what are the questions we can answer using the analysis when you apply normal distribution on the data set? So the first question is, what is the expected daily rate of return for these stocks? So which stocks have higher risk or volatility as far as daily returns are concerned? And then, so we want to understand the stocks has a higher probability of making daily returns of 2% or more. That means the profits. So more than 2%, 2% or more than 2%. Out of these two stocks, whatever the stocks that we have considered, BML, Glaxo. So which of these two stocks more than 2% profit? And similar way, so which stock has higher probability that making a loss of 2% or more? Loss of 2% or more. Which stock out of these two? So that is what we want to find out, right? So let us see how we can apply this normal distribution concept on the data set to find the answers for these questions. The first step is compute something called as a variable or a parameter called gain. So how do we compute gain? The gain is close price minus close price of the previous day by close price of the previous day. That means, let us say for example, so this is my close price for a stock. Let's say for example, this is BML stock price. This is the date, and this is what actually we want to compute, gain percentage. So how do you compute that? So this is what actually we have computed. This we have computed using 1616.80 minus the previous day close price of the stock, that is 1625.65 by 1625.65. So this is this value. That means the close price of current day minus close price of the previous day by close price of previous day. So like that, we have computed for all days. Wherever you see negative value, so that means there is a loss. Wherever you see positive value, that is gain, profit. So here we have a profit. So this is a loss. Okay, loss. Okay, profit. So this is how we can understand. And just take this gain, and if you represent in a simple line chart, you can see zigzag. So some of the lines which are going above zero, some of the lines which are going below zero. Wherever you see the lines going above zero, those are profits. Below zero, those are losses. So the same thing, whatever we discussed here. And you can observe here, so on particular day, the gains. So way high gains are there, and here the low gains are there. So we can compute this gain using this formula, whatever we have discussed. That is the close price of a current day minus close price of a previous day by close price of previous day. That is gain. And in Python, we can compute this so straightforward. So with one single method, that is PCT underscore change. So PCT is nothing but percentage change. So this is available in a library called pandas, and we'll see how we can compute it in Python as well. Right. So once you compute this gain, then I'll take that gain column. Then we are going to see the distribution of that gain column. The distribution of that gain column is this. This is for Glaxo, and this is for BML. And let us compute for this Glaxo and BML the mean values. How you can compute? So for a distribution of mean value, this is nothing but the values, right? Numbers, right? If you see here, so this is what actually we're talking about. For this column, so if you represent in histogram fashion, so if you represent this histogram, and then I'll join this, this is what actually we're talking about, the distribution, right? Then I can compute for this column mean, I can compute this standard deviation. Both I can compute for this. So that is what you can see here. This is nothing but the density plot, the distribution plot from the values that we have computed from the stock prices. Then the mean value for Glaxo is 0.0004. The standard deviation for the Glaxo is 0.0134. Right. So this is one set of information that we have got. So likewise, let us compute for BML also. The mean value is 0.0003. The standard deviation is 0.0264. So if you compare these two values, the mean value is approximately same. So there is not that much difference between this Glaxo and BML. But when it comes to standard deviation, okay, the variance, you can clearly see that the standard deviation for BML is higher than the Glaxo. That means it is 0.02. This is 0.01. Right? So that means, so for BML, the variance is more. That is clearly evident. So here also in the plot also, you see the width of the BML is more. You see the width, the spread is more. And for Glaxo, the spread is less. This is a Glaxo spread, and BML spread is this much. The variance are standard deviation, so directly proportional to the spread of the data. That is what you can see here. As the BML, the spread is more, the standard deviation is also more. The Glaxo spread is less, the standard deviation is less. Now, coming to an important conclusion here. When do you get the spread more? The values, let's say for example, okay, 5, okay, 100, 0, 200, 500, 1. If you see the individual values are fluctuating more, then you can say the fluctuations are more like this, then the spread is more. If the values are fluctuating like this, then you can say there is a high volatility. That means high risk. See, one day the stock price is at 5, then next day, that is, for example, 10, again goes back to 5, then this is 11, goes back to 6 or 7, then all of a sudden, so it jumps to, let's say, 1 rupee, then this is 15 rupees, like this. That means there is a high volatility. You cannot expect, so tomorrow, what would be the price of that? The change is also very high, and the spikes are the fluctuations, okay, the high and low fluctuations, directly translates to variance or standard deviation, and this is basically called as a risk or volatility or risk in terms of stock prices. The high volatility means high risk, low volatility means lower risk. Now here, since the standard deviation is more for this BML, this is a stock, risky stock. So in comparison to these two, so Glaxo is not that much risk in comparison to the BML because the standard deviation is not that much high. Right. Right. The same thing we have discussed here. BML stock has higher risk as the standard deviation is, of BML is 2.64. Right. And wherein the standard deviation for Glaxo is 1.33%. So that is clearly evident in the image here also. Now coming to the the questions so that we had before we start discussing about this the practical application of the normal distribution. So these are questions. Let us try to answer these questions. To calculate the probability of gain higher than 2% or more, so we have to find out the sum of all the probabilities that gain can take values more than 0.02. Okay. Now let us see this. The probability of making 2% loss or higher in Glaxo. So how do we compute that? So we are talking about 2% R loss. Now, if you recall our yesterday's discussion, if you have to find out, this is 60, we have discussed one example yesterday, and this is 70. We computed the probability that, so if you pick a student from the class, what is the probability that the student will get a score, will have the score less than 70. So this is what we have computed. For this, we have found out the area to the left of 70. Same here also. Here we're talking about the loss. Loss I can represent minus 0.02. Okay, loss minus 0.02. Then what we want to find out? The probability of making the loss of 2% or higher. That means, so if you see here, so for this Glaxo, the Glaxo is this blue one, Glaxo. If you say this is where actually you can mark 0.02, then which area we have to find out? 2% or higher. That means left of this negative. This area we have to find out. So this area gives me the probability of making 2% or higher loss. So if anyone has Glaxo on a given day, that is how much it is? 6.3. The area to the left of this is 6.3. Right? And similarly, let us compute for the probability of making 2% or loss higher. So this BML. The same thing we have to compute. So this is negative 0.02 and mark this area. Now you can easily expect that since the area is more, the probability will also be more. That is what we discussed. So this is 22%. You can see here 22.3. That means, so the BML has a higher probability of making 2% or more loss. Okay, so that is loss. Now coming to profit. So which stock has a probability of gaining a profit of 2% or higher? So let us talk about the Glaxo first. Now we are talking about the profit. That means 0.02. The probability of X more than or equal to 0.02. This is what we have to find out. So for that, let us mark. This is 0.02, for example. Now we have to find out the area to the right of 0.02. So this area we have to find out. So this area is 7.1. 7.1%, right? All right. So then similarly, let us find out for the stock also. This is a BML. Extend this line here, and now we have to find out the area, all this. So this area we have to find out. So how much is area? 22.76. Yes. So this is the area. That means this is a probability that so one can make the gains of 2% or higher. So in this BML. Now, if you compare these two, so if you compare these two stocks, in the BML, loss probability also is higher. Even the gain probability, the profits probability is also higher. That means, so there is a high chance, so one can make profits or loss. So that is why this is the high risky this stock. And in Glaxo, so the profits also, the probability of making profits also low, and probability of making loss also low, that is 6.3 or 7.1. Yes, so this is not so risky stock. So if you are not a risky investor, so probably you can choose this Glaxo. So that's how we can analyze the stock prices using this normal distribution. All right. Okay. Now let me show you how we can compute all these things in Python. Yeah. Yeah, just give me a minute, guys. Sharing my screen again. All right. So now let us see how we can compute all those things, whatever we have discussed for these two stocks. So let me import the necessary libraries. Pandas. So this is a Pandas library. So Pandas library is used to pre-process the data. So whatever the pre-processing, so that we have discussed, like computation of new column, okay, and so getting the required columns, okay, and also for plotting purpose. So we have to modify the data a little bit. So all those things we are going to use this library in Python. So we are going to import this library pandas, as means alias name, and we are referring pandas as a PD. And wherever you see PD in this program, that means we are referring to pandas library. And as well, we are going to use NumPy also to somewhere we are going to use this NumPy functionalities, and we are referring that as NP. Right. So this is the command pd.read_csv to load the data. So this data set is available here, and I want to load that into programming. So BML is a dataset name. So PD means pandas, read_csv. That means we are going to read the CSV file into the Python programming. Right? And once we read that, I want to see the first few rows of the file, the first 5 rows. Right, the same data, whatever we have seen, the date, open, high, low. This is a day open, day high, day low, the last, the price, close price, then the trade quantity and all these things. Out of which, what we need, I need only the date as well as the close price, this price. Okay. Okay. Similarly, let us load the other stock, the prices also, the Glaxo. Right. So now, as we discussed, I need only the 2 columns from the data set. One is the date column, the other one is the close. So just let us extract only those 2 columns from the data set. Right. Now let us see the data set. This is the required columns. So these are the required columns that we have extracted, and we have stored that in BML_DF. This is my data set name. And similarly, we have Glaxo_DF. This is a data set name with the required columns. This is a little bit pre-processing, that is fine. Now we are going to visualize the data using a library called cbon. Cbon is a library for data visualization. And also we're going to use one more library called matplotlib. These two libraries are going to be useful for us for the data visualization. So what we are going to visualize here? Yeah, so we are going to visualize the Glaxo data. So this is a Glaxo, the stock price, how the stock price is. Right? So from 2010 to 2017, so it is increasing, little bit decreasing, but continuously, if you see, so there is a good positive trend. It is going upward, right? So bearing a few months in the end, so from 2016. So otherwise, so this is steadily increasing the stock price, right? So likewise, let us plot for the BML. So BML, so as we have already seen, this is high volatile. The stock price, it is going down, then it is going up, then going down, right? So a lot of fluctuations are there. So this is where actually we have got the high variance in comparison to the earlier, the Glaxo stock price. Then we are going to find, compute this PC transport change, the gain column. So this is the column we are going to compute. Right, then let us plot it. This is the gain column for Glaxo. Similarly, we can go for the BML, but let us see now here the density plot, the distribution plot for the gains. So this is a distribution plot, and similarly for BML, right? Now we are going to find out the mean value. Okay, mean for the Glaxo. So how do you find out mean in Python? So there is a method called mean, and this is my data set. And the data set we are going to apply mean, and even the standard deviation. So the method name is std, standard deviation, comma 4 means, so it rounds off the decimal values. So it rounds off the decimal values, so till 4 values. So that is what round, you see round, then we are computing the mean value, then comma 4 means, so the decimal values are allowed only 4. Yeah. So mean is 0.0004 and standard deviation is 0.0134. That is what we have discussed, right? So similarly, let us find out for BML. Okay. Now we are going to find out the probabilities. So of making 2% or higher loss, so in Glaxo. So how do you find out? So as yesterday we have discussed, we'll use something called as SciPy, scientific Python. And in that we have a module called stats module, stats.nar.cdf. And I want to find out the area to the left of minus 0.02. So this is this area. Right? So this is negative 0.02. I want to find out this area to the left of. So yesterday as we discussed, if you use this command, so stats.norm.cdf, so we will get the area from minus infinite to that value, and this area will compute. So that is what we can give here, negative 0.02, then mean, then standard deviation. So these are the values that you can pass to this method, then you will get the output here, the area. So that is 0.063, that is 6.3%. And then probability of making 2%, okay, gain are higher. Now here little a change, so that is required here. Now what we need, so I need the probability of making 2% or higher, 2% or higher gains. This is 0, this is 0.02. So if I use, for example, stats.norm.cdf, okay, start.norm.cdf 0.02, comma, mean value, some value is there, and the standard deviation. So if I use this command, so which area I'll get? So this area I'll get from minus infinite till 0.02. But which area I want? I want to find out the area which is more than 0.02. That means higher gains. So this area I want to find out. So how do you find out this area? So you can find out this area using this command. And I know this entire area is 1. And simply if I subtract this 1 from this area, then I'll get this area. Right? So that is what we are doing here. 1 minus. So if you subtract this area, then the resultant area is this. So that is what I want. So that is where we have used 1 minus the stats norm CDF 0.02, the mean and standard deviation. Then I'll get this area. Okay. So that is 0.07. 7.1% is the area to the right of 0.02. That means there is a 7.1% probability of making 2% gains or higher in Glaxo. All right. So this is the exercise assignment for you guys. So you have to compute 2% loss or gain for BEML. So for this you have to compute. Okay. Yeah. So these sheets will be sent to you via Google Drive. So you can try this. Okay. Okay. So that's how we can apply the normal distribution for a practical problem. All right. So just give me a minute. Okay, so a few questions. Just I'm going through the live chat here. These videos will be available forever in the YouTube, so you can go through that even after 20 days or whenever you want to go for. Right. So if you want to access the previous classes, so you can check in our YouTube channel, right, and you will get those videos. And I would request, so all of you please join in the Telegram app. The link will be provided by our team. So please join in that group. Yeah, already it has been posted. Please join in that group. So we are going to send a lot of content. So in that. Okay. Now we are going to discuss about the inferential statistics. Okay. So if you recall our discussion on the first day, so we said that statistics are two kinds. One is descriptive stat. The other one is inferential statistics. So descriptive statistics, that is what actually we have been discussing. The descriptive statistics is so analyzing your sample data by applying numerical methods as well as visualization methods. The numerical methods includes applying mean, okay, median, mode, right? And a variance, standard deviation, range, the visualization techniques, so all those things. So when you apply on the data set in order to understand your data, so that is called as descriptive statistics. Now we are going to discuss about inferential statistics. First, let us see what is this inferential statistics all about and why do we have to apply this. Then we'll discuss the different techniques that are there in the inferential statistics. Let us say, for example, we want to find out the average height of Mumbaikars. So that is what I want to find out. Okay. Let's say, for example, this is the population of Mumbai. All the people are here, right? And how do you find out the average height of the Mumbaikars? So the brute force method is so just go and collect each and every Mumbaikar's height. So go and ask. So all the people who are living in this Mumbai city and collect their height details, person one. So let's say some height, person two, person three. So just collect all of these people height. Then once you get this height, then collect the just take the average. So that's how we can compute the average height of Mumbaikars. But is this feasible activity? For this, we have to spend a lot of money and time. But first of all, why would they give their height? If you ask them, right? So that is a difficult task. But is there any way uh, that can we estimate the average height of Mumbaikars? Yes, we can do that. So that is through inferential statistics. What we can do is, I have a population here. So all I want is the average height or average weight of this population. Let us talk about India. Okay? So I want to find out the average weight of Indians. So that is what I want to find out. Now, what we can do is I can take the sample from this data, a representative sample from this data. Okay, so this is sample. So this sample is a representative of this population. Then we will apply inferential statistics on this sample data. Inferential statistics on the sample data. Then, so using this inferential statistics, we can estimate the population parameter. What is the population parameter we are trying to understand here? The weight, average, okay, Indian weight. So that is the population parameter here. Using the sample, so through this inferential statistics, so we can estimate. When I say estimate, so kind of a range. So the average Indian weight so would be within these values. Let's say, for example, so 60 kgs to 80 kgs. So this is what actually average Indian weight. So like that, we can estimate the population parameter using this sample data. So this procedure is called as inferential statistics. So in a nutshell, inferential statistics is all about commenting about the population parameter or estimating the population parameter using the sample data. Okay? So that is what the inferential statistics is all about. So why do you have to go for? Because you cannot access. So it is not feasible to access the population data and compute the population parameter, right? So for that, so we will go for the sampling, and sampling is a representative of the population. On this sample, then we will apply this inferential statistics. Then we'll go ahead with this, the population parameter. Now, so the real life example here is the coronavirus vaccine, the corona vaccine. Right? So while testing this corona vaccine, so the vaccine manufacturers, they want to see actually whether this vaccine is efficient, so enough to reduce the load of the virus. Are there any side effects? So if we give this vaccine to the people, that is what they want to study. Now, if they want to study that on the population, then this vaccine has to be given to all the people who are living in this country, right? So the vaccine has to be given. Then they have to study the side effects or the efficiency of the vaccination. But is it feasible to give the vaccine to all the people? No, that is not a feasible activity, right? What they have done, so they have started clinical trials. First level, they have taken some 10,000 or 20,000 people. So once they are satisfied with the results of this, and the first level, then the proceeded with the second level. Here we have taken some 30,000 people. Then the third level, final level. Let's say, for example, here 1,50,000. Right? So that is how they have tested. Once they have tested it on a sample, then they'll apply the inferential statistical methods. Then they'll comment about the population. Okay, so on this sample, so the these vaccines are giving satisfactory results, and so it should also give us the satisfactory results on the population. So that is the inferential statistics usefulness, right? So they cannot, because they cannot access the population data directly, and they can't do this population data. So instead, they'll go for the sample data. They'll test this on sample data. They'll collect some data, and this data they'll analyze using this inferential statistics. Then they'll comment on the population. Hey, even if you give this vaccine to the population, so you would not see any bad effects. So this would reduce the virus load efficiently. So that is what the inferential statistics all about, right? As part of this, we are going to discuss confidence intervals. Then we are going to discuss about hypothesis testing. Right. So these two methods that we're going to discuss as part of this inferential statistics, right? Okay. So before we get into these statistics, inferential statistics, so we have to understand few aspects of the population and sample. Let us discuss those things. Then we'll get into this confidence intervals. Yep. As we discussed, the inferential statistics all about commenting about the population parameter. The population parameter is nothing but the mean or variance. I want to find out the average height of this population or average weight of this population. So how we can do that? Randomly select the sample, and this is my sample. Okay, I've selected randomly the sample. As we discussed, sample is a representative data points from the population. On this, so we would apply inferential statistics. So inferential statistics, then I'll get the mean value. The mean is nothing but the average height. Average is nothing but the mean, right? So the average height of this population or the average weight of this population, that is what we want to estimate. You see how we have arrived the population parameters, estimation of the population parameter using the inferential statistics. Right. So now we are going to discuss something called as sampling variation. Okay. So let us repeat that earlier example. I want to find out the India average height or average weight, for example. Okay. So I have taken a representative sample here. This is sample one. That means sample one means, so here we have collected. So let's say 1 lakh people height. This is what I want to find out. First person, okay, 5.7, second person 5.9, so that person 5.1, like that. So we have collected the details. So if I take average of this, that is, for example, I have got the average, so is 5.7. So 5.7 is the average of the sample one. Now, can we say that the 5.7 feet? Okay, so this is 5.7 is the average height of the Indians. Can we say that? Just post your responses in the chat window. Can we say that the average height of the Indians is 5.7 based on the sample that we've collected? Okay, the responses, I'm waiting for the responses here. Great. So, no, you cannot say that 5.7 is the average height of the Indians, because so if you collect a different set of sample, for example, if you collect different set of sample like sample 2, we cannot give any guarantee that the same average would be repeated here also. Here I might get a different value. Let's say, for example, 5.2. If I collect one more value, let's say one more sample. If I collect one more sample, so this is sample 3, I might get a different value here, right? So if I change the sample, I might get different average altogether. So that means based on the sample, you cannot conclude the things. Based on the sample mean, you cannot conclude the things as we discussed. Now, one important aspect about the sample mean. So this is what is this? This is sample mean, right? Yeah. So one important the phenomena of the sample mean. There is a quantity, for example, a quantity, a value. So like sample mean. So this value is taking multiple values. Sorry, let me put as variable. There is a variable. So this variable is taking multiple values. And so there is a likelihood for each of this value. There is a likelihood, chance. There is a chance for each of these values. So what is this quantity called? A random variable. Random variable. So the sample mean is also random variable because you see sample mean is taking different values. For S1 it is 5.7, S2 it is 5.2, S3 it is 5.9. That means the sample means the values are changing and we can assign the probabilities also. Out of these three, what is the probability of getting selected this S1? 1 by 3. For this 1 by 3 because you have only 3 out of these 3. What is the probability of selecting S1? 1 by 3 and 1 by 3. That means the sample means are sample mean is taking multiple values, that is 5.7 and their probability of 1 by 3, and here we have 5.2, again the probability is 1 by 3, and 5.9 the probability is 1 by 3, right? So that means sample mean is taking multiple values. For each of these values we can associate a probability. So this definition is nothing but random variable. That means the sample mean is a random variable. Very important, guys, right? Now, based on the random variable, can you take a decision? No, because random variables are there is a lot of uncertainty is involved in the random variables. You can get some idea so about a situation, okay, but you cannot conclude the things based on the random variables. The sample mean is a random variable and you cannot conclude the things based on the random variable. You cannot say the 5.7 is the average height of India, right? Okay, great. Now, one more important aspect, very important in the inferential statistics. So that is central limit theorem. Okay. What is the time now? All right. So it is 6:50. Let us take a 10 minutes break. Okay. After that, we are going to discuss about central limit theorem. Okay. Right. Okay. So there are a few questions. I'll answer these questions after the break. All right, so let us continue our discussion. There's a question if you have the whole data. So why to choose sample and calculate sample mean? So if you have whole data, then you can go ahead. And we are discussing a case where you don't have any the whole data set. So as we discussed the clinical trials, right? Is it possible for the healthcare companies to give the vaccine to entire population to check whether the vaccine is working fine or not? They cannot access to the population, right? So it is not feasible for them. So they cannot produce. So at least 100 crores the doses if they want to test it on the Indian population. It's not feasible. Yeah. So that's where we're discussing about the sample, the inferential statistics. Yeah. So there is another one. Yeah. So yesterday, okay. Yeah. So 1 or 2 days, even if you don't give the attendance, that's fine. No problem. Okay. Yeah. And still, if you want to mark that attendance, so just you can write to us. So you can give your mail ID. So then we'll mark your attendance. So that yesterday's attendance. Yeah, this is for learners nest. Yeah. So please, send us your mail ID so that we can mark your attendance. That's fine. And people who are, very much interested in attendance. So people are asking attendance link. Just focus on the concepts, guys. Leave it, the attendance and other things, certificates to us. Okay. So please focus on the subject. All right. Now we are discussing about the central limit theorem. The central limit theorem states that the distribution of the sample mean, the distribution of sample mean will be normal when the distribution of the data in the population is normal. Okay. So this is the first statement. The second statement is the distribution of sample mean will be approximately normal if the distribution of the data in the population is not normal. Okay. So if the population size is fairly large. Now let us understand what are these two statements are. So the central limit theorem states that what is the distribution of the sample mean? What do you mean by sample mean? Let us say I have the population. So this is my population. Assume that we have taken a sample. This is my sample. So let me give you the terminologies here. Sample means the group of data points, observations. Group of observations. That means sample means, so it can have 30 data points or 50 data points or 100 data points. And how many data points are there? That is called as sample size. Sample size is number of data points in a sample. Number of observations so in a sample, right? Yeah, that is the sample size. Now, when you say that this is sample one, that means in this, let's say for example, 100 observations, that is sample size is 100. So for this 100 data points, I can compute the mean, right? And let us call that as mean one. That means for 100 data points, just you have computed mean, and that is a mean one. Likewise, let us take one more sample. This is sample two. And for this also, so I've computed mean, then that is called as mean two. Then like that, we have taken multiple samples, sample n. And this is m n. Now the central limit theorem states about these sample means. What is the distribution of these sample means? If you see the distribution is normally distributed. Because this is a single number, right? So this number is 5.7, okay, 3.2, 5.9. So like that, these numbers, so I can build the histogram and I can see the density plot, the distribution plot. The distribution of the sample means so will be normally distributed if the population is normal. If the population distribution is normal, then your sample means would be normal. That is the first condition. So this one. The second condition states that even if your population distribution is not normal, still if you follow this process, your sample means would be approximately normal. Approximately normal. So that is what the central limit theorem states. That means irrespective of your population distribution, if you take several samples and their means, the sample means distribution would be normally or approximately normally distributed. It does not matter what your population distribution is. Let me demonstrate this for you in an Excel sheet. Let me open an Excel sheet here. Just give me a minute. Right. So now we are discussing about the central limit theorem. Okay. So let me draw. So let me draw some sample from the population. So let us say, for example, this is sample one. So a data point. So let me draw a few more data points in this sample. Right. So this is sample one. How many number of data points are there? 104 data points are there. Fine. And let me draw similarly a few more data, few more samples. Right. Some 3,770. So these many samples we are going to draw. Right. So we have got the samples. Now what we do is we are going to compute the mean, sample mean. Okay. So average of the first sample. So this is my sample mean. First sample. So likewise, let us compute for all these 3,700 plus samples. Means let us compute. Yeah, this is sample means. Now the central limit theorem states that the distribution of this last column. If you see the distribution of this, so this would be normally distributed. So it does not matter from where you have taken these samples. The population from where you have taken the population distribution is normally distributed or not normally distributed, does not matter. This always follows normally or approximately normally distributed. Okay, let me show you this with histogram. Now you can see here. Right, you see the bell-shaped curve, right? Okay, bell-shaped curve. Right. So what we have done? So I have a population here somewhere. From the population, I have taken sample and then computed mean one. That is what you see here. First mean. Computed one more. I've collected one more sample. Sample two. This is mean two. Okay, mean three. So like that. So 3,700 samples have collected. Then those many means we have got it. So 3,700 some. Then we have just distributed. We have seen the distribution of the sample mean is nothing but this. So this is so approximately normal distributed. So based on the shape that you can see here. So this is what the CLT is. Okay. Now all these inferential statistics so would be based on so the central limit theorem. So it assumes that whatever the inferential statistics we apply, we would assume that the data is a sample means and the data follows approximately normally distributed. So based on that assumption, we are going to apply the confidence intervals and we are going to apply the parametric, the hypothesis testing. Okay. All right. Let me share this. Okay. So with that understanding, let us get into the first inferential statistical method, that is confidence intervals. So confidence intervals. Now let us discuss about what is these confidence intervals and where do we use and what is the usefulness of these confidence intervals. Okay. And here if you see the confidence and the intervals, from this we can understand that interval is nothing but a range of values. A range of values, right? So that means some value here 5 and this is 10 or some values like this. Then confidence. So confidence means how much the confidence we have that certain value would lie within this interval. Whether do you have the 90% confidence or 100% confidence or some confidence, how much you have. That is what the confidence intervals. We are going to discuss how to construct this confidence the interval and how to attach the confidence for this interval. With an example, we are going to discuss. So credit card launch. So let us discuss this example and we are going to solve this example using this confidence intervals. So a university with 100,000 alumni is thinking of offering a new affinity credit card to its alumni. There's a university they want to they want to offer a credit card, a new affinity credit card to the old students. So the student base is 1 lakh students. So for that university. Now, so if you want to offer this credit card to all the alumni, 1 lakh students, so definitely you need money, right? And you need money to maintain the project also. The profitability of the card or the project depends on the average outstanding balance maintained by the card holder. That means, so if you give to 1 lakh thousand the students, ex students, so 100,000 the past students, if they don't use the credit card, then there is no money that is coming to the university to run this project. And the university have to take out their own money to run this project. That means that would be a huge loss for the university. And when do you say the project, the credit card project is running in the profits? If more and more students are using this more and more often, then so the project will get money and they can run this project independently. In simple terms, if more number of students are going to use this more frequently, then we can say there's a profitability in this project. Otherwise, if the students are not going to use this credit card, then the university has to take out their own money to run this project. That would be a loss for the university. So that is what the profitability of the project is. So just to test the waters, whether students are going to use this credit card or not, what they have done is they have launched a market research campaign on a pilot basis. They want to test it. So for that, what they have done is out of these 100,000 students, 100,000 students, they have extracted to 140 students. They have sampled, not extracted. They sampled 140 students on random basis, and these 140 students have accepted the credit card. And these 140 students have been given some time, let's say 3 months, and they have collected how these 140 students have used the credit card, their average outstanding balance. The first student, the average outstanding balance is $2,000. The second student is $1,500. Third student, $4,500. Like that for all 140 students data, so the university has got. So this is 2,000. Right. Now, once we get the data, so we have computed some descriptive statistics. That is the mean value of the average outstanding. This is outstanding balance. Outstanding balance of the student 1, student 2, student 3, like that. Then compute the average of this. So the average of this is X bar. Okay, X bar is 1990. So average of this is the sample mean is 1990. The sample standard deviation, so that is small s, that is 2833. Right? And then, so they're asking us to assume that the population standard deviation is 2,500. So from the previous launches, they're asking us to consider the sigma. The population standard deviation is 2,500. Now the question here is, what can we say about the average balance so that will be held after full-fledged implementation of the market launch? Meaning, so if we issue this credit card to 1 lakh students, what would be the average outstanding balance that they maintain? So that is what we want to answer. Okay. So let me repeat the question again. Let me repeat the entire exercise, the problem, then we'll discuss about the solution. The problem here is, so there is a university, so they have 1 lakh students, the alumni, the past students, and the university wanted to give a new credit card to these students, but we do not know whether they use this credit card or not. So if they use the credit card, then the university will get the profits. Otherwise, so they have to spend their money to run the project. That would be loss for the university. Okay. So just to test the things, they cannot give it to all the students, right? So they wanted to go for a pilot project, pilot basis. So for that purpose, they have randomly sampled 140 students from the 1 lakh students. And these 140 students have been given the credit cards, and we waited for 3 months. They started using the credit cards. And then we collected what is the first student, the average outstanding balance in these 3 months. That is 2,000. This is 1,500. This is 4,500, like that. From all 140 students, we have collected the data. Then compute the average. Average is 1990. Standard deviation is 2833. And this is something university is asking us to assume from the previous launches as a population standard deviation. Now the question here is, can you estimate the average outstanding balance that would be maintained by these 1 lakh students if we given them the credit cards? That means just assume that we have given the credit cards to all these people, all these 100,000 students. What would be their average outstanding balance? Would it be $2,000 or $5,000, or what would be the average outstanding balance of these 100,000 students? Okay, so that is what the question here is, right? So I hope you have understood the question and what we are trying to solve here. Now, my question is, see, already we have taken these 140 students, data and we have computed their average outstanding balance, can't we say that this 1990 itself is 1 lakh students average balance? Even if we have launched this program, the credit card to these 100,000 students, so can't we say that? So this would be the average balance maintained by these 100,000 students. Can we say that? So can we say that? So just I'm waiting for your responses. Yes or no? All right. So you cannot say right. So you cannot say that. So because this is only one sample data. What if actually if you take one more sample here, one more 140, different 140. So would you give any guarantee that so these 140 students also maintain the same 1990 as average balance? No, right? Yeah. So we cannot give any guarantee. That means so it changes sample to sample because sample mean. This is what. So 1990 is what sample mean. What is sample mean? Sample mean is a random variable. Random variable has a tendency to change based on a sample, based on the probability, right? So based on this random variable, you cannot conclude. You cannot say so 1990 would be the average outstanding balance for this population because this is a random variable uncertainty. So this is where we are going to apply confidence interval. Okay, what we are going to do? So this is my population. From this population, we have taken one sample. This is 140. And from this, we have got the statistics. Using the statistics, we are going to apply inferential statistics. This is descriptive statistics. So we are going to apply inferential statistics, which is nothing but the confidence intervals on this. And we are going to estimate the population parameter. That means for this 100,000 students, what would be the average outstanding balance? That is what we are going to estimate using confidence intervals. And that is what the methodology of inferential statistics, right? Yeah. So the interval estimate of parameter, right? Interval estimate or confidence interval is nothing but so point estimate plus or minus margin of error. Okay? So margin of this is a formula for confidence intervals. Right. So the interval estimate is nothing but the point of estimate is nothing but x bar. X bar is nothing but the sample mean. Let me rewrite here if it is not visible to you. X bar, the formula for confidence interval is this. X bar plus or minus Z 1 minus alpha sigma by square root of n. So let me explain what are these terms in this equation. So x bar sample mean, right? And then Z. Z is Z score, Z value. So I'll explain you how to get this Z value. And this 1 minus alpha, you see 1 minus alpha subscription, that is 1 minus alpha is called as confidence level. This is what the confidence level. Sigma. So sigma is population parameter. Population standard deviation. So n is sample size, number of data points in the data set. Data points are observations. So these are the terminology. So in this equation, right? So out of this, what we know sample mean from the problem statement. I know the population standard deviation. I know number of data points, so that is 140. But I do not know what is this z value is. Yeah, z value I do not know. I don't know what is this. Okay? So this 1 minus alpha are the confidence level. So generally, so we will use these values 95%, 99% or 90%. So if at all, in the problem statement, so this 1 minus alpha confidence level is not given to you. So you can safely assume that this 1 minus alpha is 95%. So mostly in the industry, we would use this 95% confidence interval. Okay, if it is not given to you, you can directly go for 95%. Okay. Now coming to Z, we'll discuss the way to get this Z value. Okay. Now, now let us plug the values into this equation. So when you see this equation x bar plus or minus, that means we will get two terms. One is with minus, the other one is with plus. That means x bar minus z into 1 minus alpha sigma by root n, then x bar plus that value. So I'll get a value with this, I'll get a value with this. That means, so a lower value here, and this is upper value here. And what all the 1 minus alpha is here is, this is basically called as confidence level. That means 95% confidence level. This is 95% confidence level. So like that, we are going to compute the confidence level or interval for a given data set. Right now, let us compute for the credit card problem. Right. So for a 95% confidence interval, x bar. So let me write it quickly here, x bar plus or minus z into sigma by square root of n, z1 minus alpha 95%. So x bar, what is x bar? 1990 minus z for 95% confidence level. So z is basically, we have a z tables, So these are the standard tables. So you can get these Z tables in any standard textbook, statistics textbooks. Okay, you can find them in the appendix, or you can also Google it, Z table. You will find this standard table. Okay, so for a 95%, okay, so the value is 1.960. So this is what 95% we are going to compute. The value is, this is a standard value 1.960. That means 1.960 into sigma by root n. So sigma by root n is 211.29. So this is the lower limit. The upper limit is 1990 plus 1.960 into 211. Right? So when we evaluate this, so we'll get the values. I think here we have computed. Yeah. So this is 1576-2404. The value is 1576-2404. So this is the confidence interval. So for the credit card example, so with a 95% confidence level, then how do we interpret this? The interpretation goes like this. Okay. So if you have given the credit card to 100,000 students, so if you have given the credit card to the 100,000 students, their outstanding balance, the average outstanding balance, so would be between these two values. It would be so $1,576 to $2,404. It would be between any value, so 1576 to 2404. Right? So that is how we can interpret this. Now from the university side, if this value is fine for them, okay, the 1576, even the average outstanding balance is $1,576. So still, if this number is fine for the university, they can go ahead and they can launch the program or the credit card to all the students. So if it is not fine for them, then they'll scrap it up. Right? So that's how, so they can take the decision based on this inferential statistics. So what we have done here now, I have a population. From the population, I have taken a sample that is 140. So from this sample data, so I have estimated the population parameter. I've estimated population parameter. So this estimated population parameter is in between these two values, that is 1576 to 2404. The population parameter is in between any of these two values. That means, so if you launch this program for all these the students, so their average outstanding balance would be between these two values. So that is what the inferential statistics, that is confidence interval, we have achieved that. We have solved this problem. Okay. All right. Okay. So a few questions. What is alpha? So alpha is called as type 1 error. So that we'll discuss more in detail in the hypothesis testing. What is alpha? For the time being, please so hold on until then. How do you understand this? Is basically the management would decide the how much confidence you want to have on the number, okay, on this interval, whether I should have 95% or 90% or 20%. How much confidence do you have? So I can have on this number. So that is what actually the 1 minus alpha is. Alpha is basically type 1 error that we'll discuss in the hypothesis test. Now, so one more thing. So why do we have to stop at 95% only? See, if we have more confidence, then that is good for us, right? If you have more confidence, yeah. So why only 95%? Yeah, that is a question. Why 95%? Why can't you go for 99%? Or why can't I go for 100%? Now let us discuss one example here. So here we have computed for 95%, right? So 15, 076 and 2404. This is the value we have computed. Now let me give you an example here. Let's say, for example, I want to go out and play. Yes, I want to play cricket. So tomorrow, let's say, for example, if the weather is good weather, let's say, for example, around 30 degrees, probably I want to go out and play. So this is what actually, so my convenience temperature. So for me to play outside. So for that, I'm looking the weather forecast. One channel, just I was checking in one channel, the weather forecast. So says like this: hey, tomorrow's temperature is 30 degrees with zero confidence. That means 0% probability. Tomorrow's temperature is 30 degrees. The second, I change the channel. In the second channel, the weather forecast man. So that guy was telling, hey, tomorrow's temperature is minus 150 to plus 150 with 100% confidence or 100% probability. The third one, I change the channel again. So the other channel says that, hey, tomorrow's temperature is 27 degrees to 32 degrees. So with, let's say, 90% probability. Now tell me, out of these three scenarios, which scenario will be useful for us to take the decision? Scenario one, or if first option, second option, third option, which option would be useful for us to take the decision? Obviously third option, right? See, if you go with this 30 degrees first option, the people who are telling this to you, they don't have, they themselves does not have any confidence on this number. Just out of the random, they are saying that. Even if you ask, 5 years old guy, hey, what would be tomorrow's temperature? That guy will just say, so about something. Okay, so like 25 degrees or 25, 30 or whatever it is. So like this only. If you see this zero probability means, so just there is no chance that this number is going to hit, the temperature tomorrow, right? And other case, so the confidence is 100%. The probability is 100%. Fine, but what about this value? The tomorrow's temperature is minus 150 to plus 150. Yes, obviously, right? Tomorrow's temperature definitely will be between in India or in Bombay, definitely it will be in minus 150 to plus 150. Further, do you have to refer to our any newspaper or channel, right? So that means the range is very high. Everyone knows that tomorrow's temperature will be between these two. Even if you say that with 100% confidence, no one would take your value because this is useless. You cannot take the decision based on this, right? And coming to this, so tomorrow's temperature is 27 to 32, a precise, concise interval with a decent confidence. Though this is 90%, still this is useful for me. Okay, 27 to 32 means yes. So within that range, my the convenient temperature is there. All right. So though this is 90%, still this is very useful for me. So I can take this and I can take the decision based on this. That means so if you have low probability or the confidence, even if you have very high confidence, things are not going to work for us because so the probability zero or the confidence zero means that is not going to work out for us. If the confidence is higher 100%, this is good for us, but what about the interval width? The interval width is very huge. That means so we have to strike a balance between the interval width and the confidence level. So that is where we'll go for mostly 95%. So this is where actually most of the companies or the clients would ask us to consider the interval for this 95% or 90%. So if you go for 99, so definitely the width would be very huge. So if you say the width is huge, that means a lot of uncertainty here. What is the issue with the width? If the width is more and more, that means the uncertainty is very high. That means your population parameter so can be any value between these values, any value. That means more number of values means more uncertainty. So that is the reason. So we cannot or we will not go for the higher confidence. Okay. Okay. So now we are going to discuss about one more important concept. Right. So we are going to discuss about one more concept. Is so what is the interpretation of the confidence interval? How do you interpret this the confidence interval? So when you say 95%, so are you saying that the mean balance so of the population lies in this range? So are the mean balance so in this range 95% of the time, or 95% of the alumni have balance in this range? So all these are wrong. Okay. So some people would interpret that, hey, this is the probability, or 95% of the alumni they'll have the balance in this range. Okay. Mean balance of the population lies in this range with 95% probability. So all these are wrong. What is the right interpretation of the confidence intervals? Let us discuss. So let us say the population is this. Right. So this is a population 100,000. Right? And just imagine that you already got to know that this population, yeah, this population, the average outstanding balance. So you already know this. So let's say, for example, that is 2,000. Okay, so $2,000 is the average outstanding balance of this population. Just assume that this you got to know. Okay, now right. So then what we do is I'll take the samples, multiple samples, So I'll take sample 1 from here. This is my sample 1. So when I get a sample 1, using a sample 1, I can construct a confidence interval, right? So I'll construct a confidence interval with this sample 1, the same way how we have constructed. The first sample, with this I've got the values like 1600 lower limit. The upper limit is 2200. So similarly, I've collected one more sample. Okay, so this sample 2. So this sample 2, the value is like this. For example, this is 1 and this is 2. So with this, the value is like this. This is 1800 lower limit. The upper limit is 2500. And I've taken one more sample, sample 3. So this sample 3, so the value or the interval is like this. So 2100 to 2700. So like that, so have constructed lot of intervals. Like let's say for example, so 100 intervals have constructed by taking 100 samples. So the fourth one, let's say for example, so this 1500 to 2100, okay, and let's say 50th one, for example, so this is 1400 to 1900, so like this. So this is 90th one, okay. So this is 1800 to 2500 again. So then, so 100th one, let's say for example, so to 1900, 2600. Right. Now, see this. The first one, this is one interval that we have constructed, confidence interval with 95% confidence interval. Let's say for example. The first one, so this interval has the population parameter. What is the population parameter? 2000 is a population parameter, right? So the first interval so has the population parameter between these two values, that is in the interval. That means the first interval contains the population parameter. This is good because 2000 will be in between somewhere, right? 1600 to 2200 between these. The second interval also has the true population mean, that is 1800 to 2500. The true population mean so has this interval. Then what about this third one? The third one missed. The third interval missed the true population mean. That means so the lower interval started from 2100 and 2700. That means this missed the true population mean, and this contained, and this also missed the true population mean. Okay. So like that, so the true interpretation of 95% confidence interval means if you take several samples like this. So if you had constructed the 100 intervals, out of 100 intervals, so at least 95 of such intervals would contain true population mean, would contain true population mean. So like this. So that means so five, okay, so 5 intervals would miss the true population mean. So which of those 5 we do not know. We don't know which of those 5. Okay, so that is where actually so 95% when you say so at least 95 of the intervals out of 100 if you construct so would contain the true population mean and 5 would miss. Now what happens when you increase the confidence? So let's say for example if you say 99% the confidence level. So how do we interpret that? So at least 99 of those intervals would contain true population mean. Here what is the true population mean? 2000 is a true population mean. So what happens when you go for 99% interval? That means the width would increase. That's what we discussed, right? For 0, 30 degrees, and for 100%, if you increase in confidence, so there is 152 plus 150. That means the width would increase if you increase the confidence. when you increase this confidence, the width would increase. That means, so this would be widened. This would be widened. So this also would widen, right? So that means, yes. So this, whatever the intervals that have missed the true population mean in case of 95% confidence interval. So now those intervals would contain the true population mean because of the wider bit when you go for 99%. So that is how you can interpret that when you build this 99% confidence interval. So 90 out of 100, 99 of such intervals would contain true population mean. Okay, so even that goes for 90% also. 90% means 90 of such intervals would contain. So because the interval width would decrease, okay, this would decrease, some more would miss the true population mean. Okay, so that's how we can understand this confidence intervals. The true interpretation, the right interpretation of the interval is this. All right. Okay. Now, so now we are going to discuss about something called as a T distribution. So because if you recall the problem statement, so we have used the problem x bar minus plus or minus z, okay, into sigma by root n. So here what is sigma? Sigma is population standard deviation. Okay? Population standard deviation. But do you get the population standard deviation in all the problems, in the practical problems? No. So you will not get this population standard deviation. In the practical problems, practical scenario, you will not get this. But how do we compute the confidence intervals if you don't get this population standard deviation? Then, so we have, so if you don't have the population standard deviation, but we can compute the sample standard deviation, right? Sample standard deviation, that is smallest. This I can use. So in place of population standard deviation, then your formula. So here I want to use the sample standard deviation. So when you move from population standard deviation to sample standard deviation, so your formula also changes. From Z distribution, it changes to T distribution. That means x bar plus or minus T into 1 minus alpha, so n minus 1 s by square root of n. So this is the new formula that we'll use for all the practical problems. So sigma generally, so for academia, theoretical problems, so you can use this formula, but for all practical problems, so you have to use the T distribution, T value, and s by root n. And same, the 1 minus alpha is nothing but the confidence level, and n minus 1 is called as degrees of freedom. Degrees of freedom. So n is again the sample size. Okay, and with this changed formula, now let us compute the confidence interval. So 1 minus alpha, that remains same, that is 0.95 n. Total number of sample size, this data points are 140. So T for 0.95 and degrees of freedom is 139. Okay, T 1 minus alpha n minus 1, which is nothing but, so T 0.95, so n minus 1. N minus 1 is, so n is 140, n minus 1 is 139. 139, right? So the T value for this, again, this we can compute from the standard T tables. You can Google it, you will get that 1.98. That value is 1.98. Then simply we plug the values in the formula. So that is 1990, okay, minus T value is 1.98 into S by root n. Okay, that is S by root n is 239. So this is a lower limit, and upper limit is 1990 plus 1.98, 239. Fine, right? So this is the interval, and this is what actually will get it. So that's how we can compute the confidence intervals for a given problem. Yeah. Yeah, right. Now let us see how we can implement or how we can compute the confidence intervals. So for the stock prices that we have discussed, so for BEML and Glaxo, okay, let me show you how we can do that in Python. Just give me a minute. All right. Now let us discuss about how we can compute the confidence intervals. So for the gains, so of the stock prices for BML and Glaxo. So let us see that now. This is right. So we have loaded successfully, and let us see. So let us see what is there in this data set. Let me show you. So in this we have the close price and gain price. Now I want to compute the confidence intervals for this gain. That means if you have taken all the data, so from BM Glaxo, so the gain percentage so would be lie between which of the two values. That means the population parameter would lie so between which of the two values. That is what I want to compute. So for that we have a command, direct command. So from the scientific Python, that is a stats method. So stats.nar interval, and this is what the confidence level I want to compute. Then the mean value of the gains and standard deviation of the gains. Then I will get the value. So let us see that now. So the 95% confidence interval is this much. Negative 0.0258 to positive 0.0266. That means, so if you take the population parameter, so of this Glaxo, the gains, so that would be between these two values. So negative indicates the losses, the positive indicates the profits. That means, so it is anywhere between the negative value to positive value. That means loss to profit. This is the negative 2% to positive 2%. That is what you can understand from this Glaxo, this confidence interval. Similarly, we can compute for this BML also. So this is 0.95 and the value is negative 0.051 to positive 0.0. That means negative 5% to positive 5% is the interval in which the population parameter would lie, right? All right. So this is what I would like to cover as part of today's session. Okay. All right. And don't forget, so please join our Telegram group and you can subscribe to our YouTube channel. and we'll wind up the session for today. And tomorrow we'll start with a new topic, that is hypothesis testing. Yeah. Okay. And we will circulate. Yeah. So the data sets as well as Python codes in a Google via Google Drive, and the Google Drive link will be posted only in Telegram group. So you can access from there. Okay. Okay then. So thank you. Thanks for joining, and good night. We'll meet tomorrow. Okay. Bye for now.